flexible choice of critical constants for the improved hybrid Hochberg-Hommel procedure. And this is joint work with Gou. He was my PhD student, Northwestern, graduated about 2 years ago, and he's at Hunter College. So that's the outline of the talk. So first of all, I will state the multiple testing problem, which is a standard multiple testing problem. So we've got n hypotheses with p-values p1 through pn, and ordered values are indicated by double subscripts 1, n, 2, n, and so on for the p-values, and the corresponding hypotheses are similarly ordered h1 through hn. And in this talk, we'll assume that the p-values are independent, and we have the usual strong control requirement for the family-wise error rate, which is the probability of rejecting at least one true hi for all non-empty intersection hypotheses H capital I. So we define this HH0, where first H stands for Hommel and second H stands for Hochberg. We actually start off putting 3 H's because there was a hybrid, but we decided to just stay with 2 H's, and it's a one special case of a general class of HH step-up procedures. So you fix critical constants C1 through Cn and D1 through Dn such that Ci's are bigger than or equal to Di. And a general HH procedure is that at step I, you compare the ith ordered p-value, or I should say n minus I plus 1th ordered p-value with a critical constant Ci times alpha. And if that p-value is less than critical constant, then you reject all hypotheses whose p-values are less than or equal to Di times alpha. And so number of step-up procedures are actually special cases of this general HH procedure. So for example, Hochberg procedure, which I abbreviated as HC procedure, uses Ci equal to Di equal to 1 over I. And so this procedure is of course familiar to most of you. You start with the largest p-value Pn and compare it with just alpha, which is alpha over 1. And then if that is not significant, then you go on to the next one, the n minus 1th order p-value compared with alpha over 2, etc. Okay? And so C's and D's are equal actually. So it's a very simple procedure. And it's a conservative shortcut to the Hommel procedure. And so it can be actually improved upon. And actually, my friend Rome, who is here, actually showed a way to compute the exact values of Ci and D. The Hommel procedure is somewhat more complicated. Actually, it doesn't exactly fit in this framework because the critical value Ci's actually change for the hypothesis at each step. So that's why they are denoted by Cij rather than just Ci. And Cij is I minus j plus 1 over I. So for example, at the first step, you start with, again as usual in the Hochberg procedure, you start with the largest p-value, compare with just alpha, and at the next, suppose that's not significant. If it's significant, of course, then you reject all hypotheses. If it's not significant, if the largest p-value is not less than alpha, then you go to the next step and compare the n minus 1th order p-value, second largest p-value, with alpha over 2. So that's still same as home procedure, but at the following step, you compare the second largest p-value not with alpha over 2, but 2 times alpha over 3, and so on. So basically, the critical values that you compare the p-values with change, actually increase at each step. So if some p-value was not less than alpha over 2, but could be less than 2 alpha over 3, and so the condition is satisfied. So in that sense, the Hommel procedure is somewhat more complicated. By the way, there is another part of it, which is that if that inequality is satisfied for at least one order p-value, then you reject any hypothesis whose p-value is less than 1 over I minus 1 times alpha. So di is 1 over I minus 1. So clearly it is more powerful because the critical values actually increase at each step compared to the Hochberg procedure. Hochberg actually make a shortcut by just taking the smallest critical value. Now the H0 procedure is a, as I said before, is a special case of this general class, and actually it was pointed to our attention by, again, Roth, and he had, I don't know how you thought of it actually, Roth, but Ci is equal to I plus 1 over 2 times I. So for example, at C1 it's just 1 plus 1 over 2, just 1, and at step 2 it is 2 plus 1 over 2 times 2, so 3 over 4, and so on. So these critical values decrease slowly, and di is 1 over I, just like in the Hochberg procedure, and then Cn and Dn are equal to 1 over n. So for n equal to, so this is a H0 procedure, is a special case of H procedure. For n equal to 2, these procedures coincide, these three, Hommel, Hochberg, and H0. For n bigger than 2, H0 can be shown to be uniformly more powerful than the Hochberg procedure, and although not universally more powerful than the Hommel procedure, in almost every power simulation we found that it's actually more powerful. And it's very simple to apply, almost as simple as the Hochberg procedure. So what's flexible choice? So this choice was actually suggested originally by Rohm in a paper in the British Journal of Psychology, Statistical Psychology. This choice was originally suggested by Rohm. We did mathematical analysis of this and showed that actually this is 0th order approximation to the exact constant. So you can actually improve upon this by 0th order, 1st order, 2nd order, and so on. And also one can show that this choice follows from the condition that the CIs must remain finite when alpha goes to 0. Okay, so that's why this choice seems reasonable. However, then we realize that what we need is that the CIs did not remain finite. What remains to remain finite, and actually it's less than 1 because you want to compare the p-values with those critical constant, is CI times alpha, not CI. Okay, so if you relax that condition that CIs must remain finite when alpha goes to 0, then we have a more flexible choice. So when we remove the above condition, which is the second bullet, then the condition of the di to be 1 over I also can be relaxed, because the di equal to 1 over I if and only if Ci is equal to I plus 1 over 2 times Ci. So we can make a more flexible and hopefully a more powerful choice of this pair of critical constants Ci and Di. Now, I know this is very difficult to read, but HH procedure we showed that the step of shortcut to a closed procedure, and that closed procedure has, so remember how you get this closed procedure. So for every intersection hypothesis, you need a local alpha level test, and then if you can find, under certain conditions, if you can find a shortcut, because the closure procedure requires 2 to the power n minus 1 test in general, and you need a linear test which requires at most n tests, and if you can find a shortcut, then actually shortcut is better to apply in practice. So we showed that this HH procedure in general is a shortcut to a procedure which which is a closed procedure and uses a local alpha level test whose critical region is derive analytical results about the Ci and Di and also compute Ci and Di. Okay? So we use these recursive relationships between Ai and Di. The similar recursive relations were previously used in papers by Kai and Sarkar and myself and Janta Gou. And so based on that, we developed a computing algorithm, and the computing algorithm proceeds. So you compute CR, C1, D1, C2, D2, etc. So for n equal to 1, you fix a D1 in the region 1 over n to 1. You don't want to have D1 to be less than 1 over n, because then it will be less powerful than Bonferroni, because Bonferroni uses alpha over n. Okay? On the other hand, you can't fix D1 to be more than 1, because otherwise it will be more, D1 times alpha will be more than alpha, and So you will not be able to control time. So it has to be in that interval 1 over n over n, 1 over n to 1. And for n bigger than 2, having determined C1 to Cm minus 2 and D1 up to Dm minus 1, and I will show you flow chart in a moment, you find the next D value Dm for two limiting cases, and the Dm is not uniquely determined. So, and then you try to find the two values of Cm minus 1, that we already know Cm up to Cm minus 2, you find Cm minus. So you start with basically, you start with Cn and then Cn minus 1 and so on. So set Cm minus 1 equal to its largest possible value, Cm minus 2, and find the corresponding smallest possible value of D star. So remember that Cm minus 1 must be less than or equal to Cm minus 2, so its largest possible value is Cm minus 2, and you find the smallest possible value of D star M, because the inverse relationship between C's and D, if C is large, D will be small, and vice versa. And set C minus 1 equal to its smallest possible value, because Cm minus 1 is always bigger than or equal to Dm minus 1, so the smallest possible value is Dm minus 1, and find the corresponding largest possible value of the next value of D, which is D double star M, by solving that equation, summation of AI into alpha, that should be the type 1 error for the intersection test equal to alpha. And so you choose Dm in that interval, D star M to D double star M, according to some rule. So D again is not uniquely determined. For example, the midpoint of the interval, and given Dm solve for Cm minus 1. Okay. If a solution that satisfies Cm minus 1 is equal to Cm minus 2 does not exist, then we cannot exhaust alpha. Exhausting alpha means that the intersection hypothesis has level, does not have level, full level alpha. And so the test will not be as powerful. And so that the flow chart shows the calculation. You start with D1, if you remember, from between the interval 1 over n to 1, then to D2, then find C1, and so on. So you follow that path. So this can be easily programmed. There is this non-uniqueness in determining Dm in the interval D star M and D double star M. And actually, when D equals 0, then we are just using Di equal to 1 over I, which is similar to the H0 choice. Or if W equals 1, then Di equal to 1 over I plus 1, because we always found the value of Di to be between those two limits. And so we actually made the calculations for a bunch of values of W. Here I'm just showing you three values, W equal to 0, W equal to 0.5, W equal to 1. And if you look at, for example, W equal to 0 column, because that's the column, that's the value that we are familiar with for the H0 procedure. So Di is just 1 over I, 1 over 1 over those values are slightly different, 1 over 4. Oh yeah. Remember that H0 procedure is exactly determined, and so the CI values are like 1, 3 over 4, 2 over 3, and so on. But the values actually the values that we compute using this critical constant are not exactly H0 group values, but actually more powerful. So the paper also gives constants for W equal to 0.25, 0.75, and then we did simulation to find the optimal value of W. So we just considered 5 null hypotheses, n0 of those are true, n1 of those are false. You generate normal random variables with 0 mean for the null hypothesis and mean equal to delta for the false hypothesis, delta equal to 1 or 2. And they calculate the p-values using the probability integral transformation. And then we did 10 to the power of 8 replications per simulation. And then we looked at two types of power, F power and A power. F power is the probability of rejecting at least one false hypothesis. A power is like average power, expected proportion of rejected false hypothesis. And here are F power calculations, and I've just kind of delta equal to 1, delta equal to 2. I marked the highest proportion of false rejected hypothesis. And so in general, 1 over I plus 1, Di equal to 1 over I plus 1 is a better choice. And so just to illustrate that, we did I show you a numerical example here with 5 hypotheses and using Hochberg procedure, HH for W equal to 0, which is similar to the HH0 procedure, and W equal to 1. And Hochberg and Hommel can be shown to stop at step 4. So they go, don't reject H5, don't reject H4, don't reject H3, but reject H2 and H1 at step 4. HHW could 0 could just stop at step 2, so it does not reject the first one, obviously, because its p-value is even more than 0.05. And interestingly, HHW could 1 stops right at step 1 and rejects H4, H3, H2, H1. So that last procedure, W equal to 1, actually rejects many more hypotheses. And you might wonder why it stops at step 1. Also, that's the one that we have used in our biometrica paper. When more than one hypothesis are false, the more powerful choice is DI equal to 1 over I plus 1. I don't show you, but in a few cases, a W value between 0 and 1 is the most powerful choice. But because I did not show you W equal to all the intermediate values of W, but in few cases, W between 0 and 1 is also the most powerful choice. But in most cases, W equal to 1 is the most powerful choice. So that's my talk.
Thanks, Dr. Tamhane. So,
but that is something I didn't focus on is this exchangeability condition. So currently the calculation is under the point null hypothesis, where basically we're saying there's no treatment effect, but the treatment effect for the treatment is equal to the control. So we're not dealing with the situation where the treatment is actually worse than the control, which I think will be out of this exchangeability condition. But in terms of real examples,